Hey, let's discover E. Are you crazy? I know where E is. It's the fifth letter of the alphabet, isn't it? Comes right after D. Uh-oh. No, perhaps it's a different E. And do you realise, have you discovered it on your calculator? There is a button there. And down here is that button. And it's got this little E to the X on top. It's been hiding there all the time, so we're going to discover it today. And if you were to draw a graph of E to the X, you would find it somewhere between 2 to the X and 3 to the X. There's a sneaky little critter in there. This is E to the X. So what is this E business? E's a very, very important number in mathematics. We're going to have a look at it now, but later on when we look at calculus, we'll find an even more amazing property of E than what we discovered today. Anyway, so there are some ideas on E. E is on your calculator, and you can draw the graph of E to the X. But over here, and I'm taking this screen clipping now from Pearson's latest IB edition textbook here, and they're referring here to the fact that Jacob Bernoulli, very famous mathematician, was the first to discover this phenomenon of E, and it talks a little bit about his whole family here, so you could pause the presentation and read that. But down the bottom is the interesting thing, and that is Bernoulli first observed this phenomenon of E when studying sequences down here of numbers in connection with compound interest problems. Hey, we did some compound interest, so maybe it's time to have a look at what this E is about. Very important base of exponential functions. It's often called the exponential function when you have that base E. So let's have a look and have a look at what Bernoulli was doing. Let's consider a problem here, a very simple compound interest problem, where we start off with a principal at the beginning of our investment of $1. And we're also going to have an interest rate per annum of 100%. Wow, that'll be okay. Show me the bank, I'll be straight there. Anyway, so the amount, as we saw before with compound interest, is P1 plus R as a decimal interest rate over N, the number of periods, all raised to the total number of periods here, which would be N times T, or time in years. So, do you agree that here the multiply, well, first of all, the principal is 1. So coming over to the table here, there'd be $1 there. Then it's 1 plus, now this is the interest rate as a decimal, so it's just 1, isn't it? 100% divided by 100 is 1. If it was 10%, it'd be 0.1. And this is the number of times we're going to do it over and over again. And here then is the number of periods. So if we were to do it annually, so annually that's once a year, so N would be 1 there and it would be 1 there as well, and the number we get at the end is 2, so it'd be $2 after 1 year if we were doing our 100% interest once a year. If we did it semi-annually, that's twice a year, we would have to divide that by 2. That interest rate would become 2, and there would be 2 calculations. You can see what we're doing here. Then if we did it quarterly, we split the 100% up into 4 pieces and do it 4 times that year, and we'd have this amount, and so on as we go down there. So we can increase the number of times. We're doing it daily, hourly, minute. I think we did do before minutes. I'm not sure whether we did seconds. But anyway, as you do it more times, like this, you notice something is happening. The number here is not changing as much. Let's start it from here going down. 2.718 is common for all these, this one and this one and this one. And gradually it appears that the amount of change in the decimal, it's changing less and less. It's only changing the further out here we go with the decimal places. Hey, that suggests that if we play with 1 plus 1 on n and do it a number of times, a lot of times, like we're up to 31,536,000 seconds in a year, we do it that many times, it looks like it's tending to some decimal. Now, it's keeping on going at the moment, but there's every suggestion that this would tend to some actual value. Some actual value. If we could take n an infinite number of times. It's gradually getting less and less variable in those outer decimal places. It's zeroing in on some number. Now this, of course, is characteristic of an irrational number where we can never terminate the decimal. It's not repeating and it's not terminating. So we actually can never get there because we need an infinite number of calculations to detect it. But we can see it is converging or zeroing in on some particular value as indicated by the less and less change in those outside decimal places as we reiterate it, as we do the iteration or repeat the process more and more. So, do you get that? Let's try and do it on the calculator. So, here's the Casio. So you could go to table mode, see I've highlighted it there, table mode, and set it up, put in the function. Can you see this is the Techo way of saying 1 plus 1 on n to the n, using x's and brackets and stuff. Then you could set the calculator up to start at any n value and go up to bigger and bigger ones. Now, I've used Pearson's screen clippings here, not the Casio, because they've printed it out nicely for me. And so over in this first one over here, can you see that if we start with x or n, this is really taking the place of the n values here, isn't it? Because a variable with technology, with calculating devices, computers and calculators, a variable name is usually x, and that's the independent variable, and the dependent variable is usually y. So here we have n is x and y value is 1 plus 1 on n to the n. So we start off when n is 1 and then 2, and then when we get up to 365, it's got quite a bit of change through here, and then we might go up to 8,760, alright, and then we might go up to 525,600, and what do we notice here? The last one, the last very large value, is 2.7183. It's compared to here and here, even going up to, what is this, 3.15 times 10 to the 7. So even going up to that number, we have getting some stability here in those first 4 decimal places. We are starting to zero in on this mystery number e. We are tending to e. What is e? Well, it's the irrational number which we zero in on when we repeatedly do the calculation 1 plus 1 on n to the n. Now this is Bernoulli's findings. Very interesting. But what's more exciting about E is going to come up later on when we use it with calculus, and it just is a phenomenal result. So you have to wait for that for a little bit later in this course. All right, let's come down and have a look, and here's the definition of E, and I've already given this to you really just now, but coming from Pearson's now, we say E is the limit as n tends to infinity, so we're reading this off, limit as n tends to infinity of this expression. It is saying that as you calculate this for bigger and bigger values, it's zeroing in on an actual number. You would have to do an infinite number of calculations to actually find that number. And of course, infinity is an abstract quantity. It means the largest possible value you could ever have for that variable. So we know it's sort of zeroing in, but we'll never be able to find it. We'll always have to let E stand for that special value. And here we have it in words. The definition is read as E equals the limit of that as n goes to infinity. So E is tending to some actual value, and we're calling that the limit of that expression as we put bigger and bigger n's in there. Why do you think we've called this number E? Well, it's E for the exponential, of course. It is the most interesting base that you can make an exponential function from. So here, e to the x is called the exponential function. Not just any one, but when you use that base, that's a special base, and therefore we call that the exponential function. So e to the x, very special number. Anyway, so let's come down now, and here we're going to call the exponential function using e as the natural exponential function. And I suppose there's a reason for the word natural even at this stage, and that is the sort of natural occurrence of e as that limiting value of that exponential expression 1 plus 1 on n to the n. So it sort of come up naturally, snuck up on us there a little bit at the end of the compound interest, the multiple compound interest calculations. That's interesting. But there is another reason why e to the x is called the natural exponential or natural exponential function, or the exponential function, and that's to do with its occurrence or its properties in calculus and how it can be used to model naturally occurring growth functions. And that's a very important result. Okay, let's come down. And I've got some little problems for you, because obviously, having discovered E and seen how, or going to see how important it is later on, we're going to need to be able to work with it quite a bit. So look at what I've gotten for you here. I want you to try to draw the graphs of these exponential functions. They've all got E in them, using a transformation approach on graph paper. So the idea, of course, if you've learnt quite a bit about transformations, now, of course, if we have E as the base, that's not going to make a lot of difference, because, as you can see so far, E is approximately 2.7183, and then it keeps going. So when you draw the graph of e to the x, as you saw back on that leading screen, it's going to be steeper than 2 to the x, quite a bit, but not quite as steep as 3 to the x. It's going to look something like that. So it's not really very much different here, except because of the importance of e later on, then we want to actually be familiar with it, be able to do these transformations with e to the x. Alright, so I'd suggest pausing the presentation now and trying to draw graphs of those by hand. Maybe draw e to the x, take a couple of values, plot e to the x, and then try to move the points on your curve e to the x so that you get the transformed graph using a transformation approach. So you'll need to identify how do you get to these graphs as transformations of e to the x. That's a bit of fun for you. and then I want you to state the domain and range. We'll use an approach here of drawing the graph first and deciding upon what we assess the domain and range to be using that graph. All right, so pause the presentation now and have a go at that and see what you think. All right, we'll go on and have a look at the solutions. And here we are. This is the first one, which is e to the x plus 1. Y equals e to the x plus 1. Now, I've been a bit naughty here. I've used the calculator. So here we should have the axes labelled if you're going to present this on a piece of graph paper, and we need to have a scale here and also a scale up here, 1, 2, 3, 4, etc. And so those things have to be labelled. You can see it's going to go through the common point for exponential functions of 0, 1, because put x is 0 up here. Oops, this is e to the x. I'll just scrub that out here for the minute, because this is the graph of e to the x. So e to the 0 is 1, so it's going to go through there. It's going to have the usual asymptotes and so on. And now I want to try and draw the graph of this function. And as you can see, the x term's been changed by the addition of a constant plus 1. So that implies a -1 translation in the x direction. Do you remember that? Okay, so I need to move all the points on this curve. So here's one here. I've got to move that across -1. So that becomes the new y-intercept. So this one up here, let's take the point there. I have to move that across 1 unit. So you can see what's actually happening there is it appears that e to the x plus 1 is a sort of different steepness there, but it's not. It's only because we're moving parts of the curve from further up back. Can you see it is going to be asymptotic to the x-axis again? So what would you say the domain is? It's a set of x such that x is a member of R, no restrictions looking at domain values looking this way. We can substitute any x value into the function. The range, however, we want to have a look at that, is a set of y such that, y is a member of R, so going up and down here, looking at what y's can be achieved, but can you see y has to be strictly greater than 0? It's still got this asymptote over here where it approaches the x-axis where y is 0 but can never reach it. So that's the domain and range there. Coming on down, let's have a look at the next function, and the next function was e to the x plus 2. The plus 2 was down there. So I've drawn e to the x here again. So what you need to do is to label the axes, and then we must have a scale. 1, 2, what have we got here? 1, 2, 3, etc. So now checking e to the x, yes, it goes through the point 0, 1, asymptotic to the x-axis, y is 0. When x is 1, e to the x is supposed to be about 2.718 here. Okay, about there. And now we're going to move these points across. Oh no, wrong function. We're going to move them up now because it's plus 2. So the y function has been changed by adding 2. So this is a positive 2 translation in the y direction. So this point actually has to move up 2. So here we are. That gap there is 2. So let's take another point on the curve, and this gap here has to equal 2 units in that direction. And so each point is moved up. So what's the new y-intercept? It's still x is 0, but up to it will go through the value 3. So I've labelled those incorrectly here, haven't I? Here's 1, 2, that's 3, 4, 5. So yes, you can see clearly that's a y translation of 2. Well, guess what? We have moved all points up, including the asymptote. The asymptote was the x-axis, y is 0. Now the graph will be up at having an asymptote at y equals 2. The whole business has been moved up in the y direction 2 units, and so this is our new asymptote. So we're going to have some impact on our range here. Let's try and look at the domain. So the domain is looking this way at the set of x values. So let's state it up here. The domain is the set of x values such that x is a member of R. That hasn't changed at all. We can still use any x values right across that real number set. Let's have a look at the range, which is looking at the possible y values. So the range has changed. It's now the set of y such that y is a member of R, but now y is greater than 2 because of that plus 2 up here being a positive 2 translation in the y direction. So are you getting the idea there? They aren't too bad. Let's have a look at one that's got 2 transformations associated with it. So here again is e to the x, and the function we're drawing is e to the x plus 2. Take 1. So we've got 2 transformations there, so this is e to the x plus 2, and then subtract 1. So what are the 2 transformations? It's a neg2 translation in the x direction and a neg1 translation in the y direction. Can we see that? Well, here, still going through 0, 1, e to the x, asymptote at y equals 0, or the x-axis. Now we're going to move all the points neg2. So here, let's have a look at our scale here. This is the point neg1 for the x, neg2. And so now this intercept here, which is at 0, now goes across 2 units. So it's going to be across here somewhere. We lost the scale there a little bit. So this is going to be across 2 units. All points are going to go across 2 units. So here then, I'll just come down and have a look at that one again. So here, if we take this value here for 1 and we move it across 2 units, it should be lining up somewhere about there. Hang on. 2 units, we're not quite there. Let's come down a bit here. I think. No, can't line that one up too well on that scale. But you have the idea. You need a bit of a graph, a bit better graph than I've got there with these pixels. All points have to be moved across 2 units. So, see if we can check this out here. Points like that, all going to be 2 units in that direction. All right, what about the y values though? And that, of course, is why our scale doesn't line up too well, because here we're going to drop that point down by 1. So we've got to go across 2 and down 1. So in each case, we're back 2 and down 1. So let's just see that. That's where I was making a mistake before. That goes across 2 but down 1. So it's going to be lower down here. Got to do both of those moves, -2 and then -1. So it's going to change the position a bit there. All right, so let's have a look at what's going to happen over here. Everything's been moved in the y direction by -1, so the asymptote is going to be y equals -1 as a new asymptote. All right, so can we look at the domain and range now? Let's look at the effect on the domain. Looking along this way, are there any x values that would be excluded? No. So the domain is a set of x such that x is a member of R, and that would be it. The range, looking up and down now, what's the change in behaviour there? The range is a set of y such that y must be greater than -1 now, and y is a member of R. So it's just changing that asymptote in this particular case. So watch this one. What's that shift? -2 and then -1. And see what happens as you move a bit of the curve down. So that was my problem back here with the scale here. As you move it across -2, you move it down -1. So you will have a different part of the curve there. Well, let's look at the last one. And the last one there, just remembering this is y equals e to the x. Just label these again. And 1, 2, we've got 1, 2, 3 and 4, and then this graph will be y equals 2e to the x plus 1. So when you look at that function, you can see there are two transformations. First of all, there's a stretch by a factor of 2 in the y direction, and then there's a +1 translation in the y direction. Translation. Okay, so let's try and do that. So let's start with e to the x. Let's start with this crucial point here, 0, 1. If we stretch it, it's going to go to 0, 2. And then if we add 1 to it, it's going to go up to that point 0, 3. So that's not a bad way of starting with that key y-intercept. But you could do it with all the points. Let's see if we can do it with a half here. So, okay, when x is a half, this is our value. We would double it now. So doubling it puts it somewhere up here. And then we add 1, which puts it there, somewhere around there. That's where I suggested you use graph paper. It's pretty hard to track this out. The graphs are correct here. Casio doesn't have made a mistake here, but it's pretty hard to track out the movements. So you are stretching, so that's doubling the value, doubling the y value, and then adding 1. Let's do another one. Let's go over here at -1/2 for e to the x. There's the value, and then we double it, so we're going up twice as far to that point, if you say, and then we're adding 1, so we end up creating that point on the transformed graph there, on the new function 2 to the x plus 1. So to map a point on from e to the x onto 2e to the x plus 1, we have to do the stretch and then add 1 to the y value. All right, so these are important things to be able to do with exponential functions. That's really only a bit of revision, and what we want to do there was to make sure that you could do it with our newly found and newly discovered function e to the x, very important function later on. All right, so we're going to now get into some work with exponentials and logarithms as well. So have a look at e, think about it, and it's going to be our preferred base in the future. Very handy base e. But for the moment, it's cheers from me. I'll catch you in the next presentation.